So last time, today will be the last lecture of the two-round part, and on Thursday we will start the extremal set theory. So last time we introduced Sidorenko's conjecture, and we proved some basic cases of Sidorenko's conjecture. This is one of the main open problem conjecture in extremal combinatorics, I would say. It says that for every bipartite graph H, the number of, so the formulation is like this: the number of homomorphisms of H to any host graph G is at least the edge density raised to the power the number of edges in H. In other words, as we mentioned last time, we can rewrite, if we use P for the edge density of the host graph G, this is P, then basically what it says is that the number of homomorphisms of H to any host graph G or bipartite H is at least the counts you will see in random graph with the same edge density P. In random graph, you have n choices for each vertex of H, and for each choice of placements of vertices of H that you map to, then for every edge of H, you will need to see an edge, which happens with probability P, independent of all other pairs. Okay. So this is last time. So today we're going to continue. Today we will continue. We'll give some applications of Sidorenko's conjecture and supersaturations. I think last time at the end, we proved a supersaturation for 4 cycles. Let me just copy paste the result here. Right. So supersaturation for 4 cycles. Okay. So the first result we will see today is a bipartite two-round results of a very symmetric graph, the 3-dimensional cube. So 3-dimensional cube. Let's write Q3. How does it look like? It looks like this. Okay, this is the 3-dimensional cube. And obviously, this is a bipartite graph. We can color its vertices by red and blue. Let's say blue, oops, blue, 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 and red, 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 red. Okay, this is a 2-coloring of 3-dimensional cube. And we know by covariance the extremal number. So let's write down some basic observation. Covariance says, well, this number should be at most n to the 2 minus some constant c. And remember this extension by Furedi along correlation Sulikov that we proved that if you have bounded degree from one side, and this is a 3 regular graph, because Q3 is regular, we have an upper bound n to the 2 minus 1 over 3 from their results, which is n to the 5 over 3, 1.666. Notice that Q3 is does not have, it's 3 regular, but does not have K33 as subgraph. So remember, there's this conjecture by Conlon and Lee saying that for any bipartite graph, if it does not contain K33 as a subgraph, if it's bounded from one side, degree 3, then we should do strictly better polynomially than this bound n to the 5/3. And 3-dimensional cube is a positive incidence of their conjecture. We're going to do a bound that's polynomially better than this. So this is what we want to prove. Wait. Yeah. So extremal number of Q3 is big O of n to the 5/3, 8/5. So the power is 1.6. We improve it from 1.666 to 1.6. So here the lower bound, embarrassingly, we don't know anything better than n to the 3/2. So for lower bound, we only have this is just coming from forbidding C4. Obviously, forbidding C4 is a much stronger condition, but and we can already achieve this many of edges. But forbidding a larger graph, the graph should be denser. We cannot do better. So any construction that will, so improving any one of these two bound by an n to the epsilon would be a very nice result. How do we prove this? So we're gonna actually prove something slightly better. We're gonna prove this Q3 plus is have the same upper bound. So what is Q3 plus? Q3 plus is this 3-dimensional cube, but with a diagonal chord. Let me draw it. With a diagonal chord, let's say this is x, this is y. So Q3 plus is Q3 plus long diagonal, as in this picture. If you can prove a larger graph has the same upper bound, of course, the smaller graph will have the same upper bound. How do we prove this? The trick is that, so here's the idea. It's a simple but nice idea. Not at all trivial at the first glance. Although if you see the idea, it seems then natural. The idea comes from a particular way of drawing this Q3 plus. So this is a small instance reflecting that sometimes for bipartite two-round problem, if you can come up with a nice way to draw it, that sometimes give you a way, give you some inspiration of how you should embed it, which could help you to prove better bounds. So the order, the way you embed the bipartite graph could affect the bounds, definitely. So here, the idea is that we're going to use supersaturation for C4. So we have a lot of full cycles, lots of full cycles. Then by averaging, just by averaging, pigeonhole, since there's a lot of full cycle, there must exist an edge E that sits in lots of full cycles. Okay, sits in many full cycles. No problem. And why is this helpful? Then what we're going to do is we look at this E, let's call it XY edge. Okay, now let's draw it in a slightly different way, in a bipartite fashion. This is the neighborhood of X, right? So let's draw it here. This is the neighborhood of Y. Let's draw it like this in the bipartite fashion. Now all we need to do is between the neighborhood of X and neighborhood of Y, we just need to find a sixth cycle. Then we are done, because this XY plus the sixth cycle between their neighborhood is exactly this graph, three-dimensional cube with a long diagonal chord. So let me highlight it and show you that this is indeed the case. So here is, let me use purple to highlight it. So we have our edge XY, the same XY here, edge, this one. I use blue, so maybe let me also use blue here. Okay, then purple C6 in the neighborhood looks like this. This is the C6 in their neighborhood. You see, these three vertices are neighborhood of X, and these three vertices are neighborhood of Y. So, and the trick is that the number of full cycles containing XY, each such full cycle will correspond to an edge between their neighborhoods. So since this edge is in many full cycle, we have many edges between their neighborhoods. You just simply apply bounded Shimonovich upper bound for 6 cycles, we are done. So let's do the calculation. That's all the idea. The rest is calculation. Recall this supersaturation results. Let me put it on the side. Okay, the first trick is that, so how many edges we have? We have this many edges, right? We need to show, so let me write it down. We need to show. So need to show for any n vertex graph G with some large constant times n to the 8/5 edges, we can find a Q3 plus in G. Remember this regularization trick of Erdős and Shumanovich by regularization trick of Erdős and Shumanovich. We may assume, let's assume, G is K-regular. Okay, meaning that the maximum and minimum degree differ by a factor of K. So let's write down. So that means the minimum degree is bigger than, let's say, C times n to the 3/5. There might be some constant factor off. Doesn't really matter. So K times delta G less than K times C times n to the 3/5. Good. So we have a a good control on the degree. Now by supersaturation, the highlighted part on the top right, we know that this graph, obviously average degree is more than square root n, has many four cycles. How many four cycles? Then supersaturation implies the number of four cycles, C4, is at least the average degree. So let's just put minimum degree to the power of 4 divided by 8. So it's at least C to the 4 n to the, so let me not do the calculation for now. It's at least average degree to the power of 4 divided by 8, right? And the number of edges is n times average degree divided by 2. So averaging implies, is this an edge? E, let's call it xy, lying in at least how many? Number of C4 divided by the number of edges, which is at least d of g to the 4 divided by 8. Number of edges is n times d of g divided by 2. So equals to d of g to the 3 divided by 4. There's an n here. Okay, so this is bigger than, let's write down what's this number. C3 n 9/5 over 4. So this is 4/5. This is the number. This many C4s. This implies, as I said, every C4 give rise to an edge. Each such C4 give you an edge in this graph between their neighborhood, implying that, so maybe let's give it a name. Let's call this G prime. So we have E of G prime is at least this number, C cubed times n to the 4/5. And all we need to show is this is above the C6 upper bound. So this graph, EG prime, has how many vertices? The number of vertices at most degree. So the number of vertices of G is at most 2 times maximum degree of G. It's the neighborhood of X plus neighborhood of Y, which is at most 2 times, there's this capital K, right? K times C times n to the, what is it? 3/5. So let's call this guy capital N. So we just need what? E of G prime, which is more than this number of edges, to be bigger than what is the C6 bound, n to the 5 capital, sorry. By bounded Schumann wedge, you need it to be this guy, right? Times some constant. I think 10 is enough. I don't remember the constant, but 10 is enough. So this is bounded Schumann wedge. If this is true, then we get a C6 in G prime, which is the same as Q3 plus in G, and we are done. I will skip the calculation here. let me just convince you. So what is this guy raised to the power of 4/3, right? The 3 cancel out, you get 4/5, which is exactly this thing. So as long as you take C large enough compared to K, we are fine. So here, require C much bigger than K, like some function K. Any question? A simple proof. Use of supersaturation. Next. We will see another applications of supersaturation and homomorphism inequality involving Sidorenko's, related to Sidorenko's conjecture, is another application of supersaturation and homomorphism inequality. This is the extremal number for the grid. So let's call GTT the T by T grid. Very simple how it looks like. Let me draw. Okay, this is a T equal to 5 by 5. Okay. Obviously, C4 is contained in GTT. We usually consider T is at least 2, otherwise just a singleton graph, right? When T equal to 2, that's precisely C4. So for larger T, C4 is just a building block of this grid. It's a smaller graph. So this implies what? Because of this, the extremal number of a larger graph can only be larger, meaning that for any T at least 2, the grid graph extremal number is at least the extremal number of C4, which we know is at least of order magnitude n to the 3/2. Now the natural question is this n to the 3/2 the correct power to guarantee a GTT for any bounded T? The answer is yes. So turns out, as long as you reach this many of edges, then you will see C4, but not long after, you also see any large size grid. So obtaining a grid is not much more expensive than obtaining a C4 in the sense of the extremal number. This was first proved fairly recently, maybe 2 years ago, or by this was first proved by Radich, Genzer, Shudakov, and Tomon, who showed that this T by T grid, the extremal number is, they also give a lower bound that can bring T also into this lower bound, is big omega of T to the 1/2 and to the 3/2. So as T gets larger and larger, we do have a better lower bound than the C4 one. Upper bound they have is exponential in T to the 5, in fact, times n to the 3/2. So that's their result. And their proof is not long but fairly involved, using some initial bound, weaker bound, and then use tensor power trick to boost bootstrap the bound to the tight one. So here we're going to present the proof, making use of supersaturation and homomorphism inequality, a much shorter proof with a much better bound. So this is a recent work of Jing Gao, also Oliver Genzer, myself, and Zixiang Xu. We prove that the extremal number of GTT discrete is at most some constant times t to the 3/2 n to the 3/2. Okay. So now we know that this leading constant should be polynomial in t. It will be interesting to determine what the power of t would be. So it will be interesting remark. What this function of t is constant. To determine the leading constants. This. Okay. So this is what we're going to prove. And how do we prove it? Let me first give you the idea. Again, as I said in the case for the three-dimensional cube, how you view this graph, how you draw it is quite important here. So let me briefly mention when they prove this weaker upper bound, how they view it is they build an auxiliary graph in which a path like this is a vertex in the auxiliary graph. And two vertices adjacent, if these two paths form a 2 by t grid, then all you need to do is to find the long path in this auxiliary graph. But you need to be careful that this path, the vertices in this path correspond to these t paths in the original graph that are pairwise vertex disjoint. All right, so there are some things you have to be careful with this approach. This is a natural way of viewing how you build this grid. You build it row by row, right, in this auxiliary graph. So what we managed to show, this much shorter proof, is if you change the way you see this grid, much better, easier embedding strategies can be used. And how we view it is, you view it like this. You have a grid. We start with a path like this, okay? And suppose the path is robust enough that we can replace it in many different ways. Then we can replace this path, this vertex, by this vertex. So it becomes a path like this. And if the new path is still, we can replace in many different ways. We can replace this vertex by this vertex. This vertex by this vertex. So we can go like this. And gradually, you grow cell by cell, you fill up this grid. And that's the idea. So let me write a little bit more. A different way of drawing a grid, growing it. Here, to make things precise, let me introduce a definition of a rich collection of paths. Definition. So here the idea, maybe let me first say the idea. Idea, use supersaturation for path to roll a grid cell by cell. What do I mean by that? Here's the definition. Let alpha bigger than 0, some natural number, and you have some k. Okay, natural number. We say a collection of paths a collection P of paths. We think of them as labeled. PK, K vertex path, a collection of K vertex is alpha rich if for any member, this path x1, x2, let's say, xk in P, and any I between 2 and k minus 1, there exists alpha, at least alpha distinct vertices xi prime such that you can replace I by I prime. You're still in this collection. So let me draw a picture. Here's the picture. For any path, so this is a path, x1 to xk, you have xi here, xi minus 1, xi plus 1. We say a collection of paths of order k is rich if no matter which path you grab in your collection, and no matter which vertex you grab in your this path in the collection, we have many ways to replace it to obtain a different path still in this collection. So we have many ways to find the xi prime such that this new path still in P. That's the definition. So why is this definition useful? Well, that's exactly what I said. You can use this collection of paths to grow this grid one cell at a time by replacing one of its vertex by a new vertex xi prime. So let me write it. This is the proposition, how we grow the grid. So this proposition is the main idea. The following proposition reduce embedding a grid to finding a collection of rich paths, a rich collection of paths. So what is this proposition? Let P be a non-empty alpha rich collection of paths of length 2t minus 2 in G in some graph. Now, if alpha is at least t squared, then G contains a copy of the t by t grid GTT. Okay, the proof is exactly I've mentioned it already. I will not write down the rigorous proof. I'll just draw some pictures. So I will draw the picture when t equal to 4. So this is t equal to 5. So proof by picture. You'll start with this one path in your collection, P, rich collection. What do I know? Since this is alpha rich, I can replace this I can replace this vertex. Okay, there are many ways to replace it. So I'm gonna do like this. There are many ways to replace it, so I can find a new vertex to replace this red one. So I switch from the original path, replace it, I grow one cell. Now I repeat this process. Okay, so now I have, let's try again. We have this graph now, right? Now I replace this guy. I know that there exists a path. So which path we apply it to? We apply it to this path. This path is in our collection P, right? What does it mean? That means this vertex, there are many ways to replace it, this path. We replace by this one. We obtain a new path. Now it looks like this. And so on and so forth. The next one, you grow like that. And then you grow like this. Okay? At the end, you grow everything. I will not draw the rest. So, all we need to do now to prove the upper bound we just need to show for any n vertex graph G, E of G more than 5t3½ n to the 3½ number of edges. We want to embed, when you have more than this number of edges, we want to embed the grid. We just need to show that in such a graph, we can find a alpha rich collection of paths of length 2t minus 2, where alpha is t squared. Length 2t minus 2 means the order of the path is 2t minus 1. All right, and how we prove this? The idea is to use the homomorphism inequality. Basically, the idea is simple. Remember, what would be a good analogy? A good analogy is we're going to start with, before we have a graph with average degree condition, because you have number of edges, we want to boost the minimum degree. How we boost the minimum degree? You say that if there's a low degree vertex, that's bad, right? We remove it and keep removing it. At the end, we prove that you must terminate at a non-empty graph. If you terminate at a non-empty graph, then by how we remove vertices, all the remaining vertices will have high minimum degree. Same analogy here. If we start with a collection of all paths of given order, if there exists a path in the current collection that's bad, what does it mean bad? Bad? That means there exists a vertex on this path and there are few replacements for it. Then we're going to delete all these paths from collection and continue. And if you can show that this deletion will terminate at the non-empty collection of paths at the end, then by definition, all the remaining paths, no matter which vertex you take, you have many replacements for it. And that, by definition, is the rich collection we're looking for. So let's carry out this more precisely. The actual lemma is this lemma. So this lemma will prove the upper bound. It says that, so let T be natural number and n sufficiently large in terms of T. And G is an n vertex graph with E of G at least 5, T to the 3/2, n to the 3/2. Then G has a non-empty alpha rich collection of P2T minus 1 with alpha equal to T squared. Okay. This is what we need to show now. We're gonna, yeah. The idea, as I said, you keep removing bad ones. Proof, yeah, let's just start proving it. Again, we have, for bipartite graphs, we may assume our graph is almost regular by this regularization trick. By a regularization trick, we may assume G is K almost regular for bipartite round problem. So we have let D to be the average degree of G, which is at least some 10 T to the 3/2 n square root n. This is the average degree. All right. Now, and let P0 be the initial collection of all 2T minus 1 paths. All P2T minus 1 in G. All the labeled ones. And how are we going to use this almost regular? Well, because the graph is almost regular, the number of such paths, P2T minus 1, so if you have a homomorphism of P2T minus 1 in G, each actual copy comes from an injective homomorphism of P2T minus 1. Because we are almost regular, most of these homomorphisms are injective. Okay, so as G is almost regular, we see that most of homomorphisms of P2T minus 1 to G are injective. Meaning, so the number of collection, the number of paths in our initial collection, there are a lot of it. Let's say most of it are injective, let's just say at least half of the number of homomorphisms of P to T to G. If this is not clear, why? Try to prove it as exercise, all right? Okay. Yeah, I will make an example. Let's say path is 4 vertex path. Each time when you grow a path, embed homomorphism, let's say the next step, you have these neighborhoods to choose the third vertex, right? And this neighborhood is roughly square root n size by our bound on the number of edges. And only a few choices are the ones that appears before. So most of the choices, if you choose it, it's going to be injective map, and you can continue. So, okay, now we're going to do this deletion process. Whenever there's a bad path that does not have many substitutes, many ways to replace one of its vertices, we're going to delete it. So we're going to define this deletion process. Officially, we will find define a sequence of collections of P to T minus 1, starting with our initial sequence, and then next collection getting smaller and smaller, dot, dot, dot. Okay, so I just need to tell you how you define from one, how you obtain one collection from the previous collection. Having defined, let's say Pi, we now define Pi plus 1 collection. So what is bad? As I said, the path is bad if you have, say, V1 to V2T minus 1. This is a copy of 2T minus 1. And let's say for some vertex in your path, there are only a few ways to replace it. The ways to replace it, less than alpha ways to replace this vertex. Then this path is bad for us. We're going to delete this path together with all these replacements of it. So, as I said, if there exists P in Pi and a vertex and a vertex A in P, such that the number of total paths P prime in Pi containing, if you are a replacement, replacing this vertex A, then you must contain these pieces with A removed, these two pieces, right? So we just need to count the number of paths P prime containing these pieces. So containing, what is it? P minus A with A removed is less than alpha, then, okay, if there exists a path and vertex such that if you remove this vertex from the path, there are not so many other paths containing this two pieces, then we're going to delete them all together. Delete all paths containing P minus A from PI. Keep doing this. Whenever you have such a bad path, remove it until, oh, sorry. If you do one step, then you get PI plus 1. And then in PI plus 1, again, if you have one path like this with few replacement, you do one step, you get PI plus 2. Each step, you only delete one path and its replacement, okay? To obtain PI plus 1. The key observation is that, so let's say the number of steps, let S be the number of steps of the whole deletion process. We need to show that we start with the collection. We need to show that at the end, when you end the PS, the S step, this collection is not empty. If there's no path at all left, we cannot build anything. So as long as the final collection PS is not empty, we are done. We need to show the final collection PS is now empty. Okay, so we need to show that we don't delete too much paths from initial collection. We already have a lower bound on the number of paths in the initial collection. By Storenko, we have a lower bound on the homomorphisms of paths coming from Storenko's conjecture. So we just need to show total number of paths we deleted during this process, not so much. At every step from PI to PI plus 1, one step, we delete at most alpha paths by definition. So all we need to do is to bound the number of steps times alpha. That will be the total number of paths we delete. How do we bound the number of steps? Observe that this is the piece, right? We delete. So let's call this path, if there exists some path, let's say PI. Okay, and let's call this piece Fi is the graph obtained by removing, so this is Fi. All these Fi in different stage, Fi, Fj are distinct copies of these two union of paths, are different graphs. Why? At every step, when we remove all the paths containing Fi, there's no path left in our current collection, Pi plus 1, ever containing Fi. So the next step, if there's another path with another Pi plus 1, that must be a different copy. These two are the different thing, okay? So as we delete all paths containing Fi at I step, all the Fi's are distinct ones. So all we need to do is So that implies what? Implies the number of steps S is at most the number of different choices for Fi. What is Fi? Union of two paths. So we just need to show the number of choices to choose union of these two paths is not so much. That's the next claim. Claim there are at most 1/4t squared homomorphism of P2T minus 1 in G possibilities for Fi. Okay. Why is this enough? Let's finish the proof assuming this claim. All right. If this claim is true, then by the claim below, the total number of paths deleted in the whole process is at most number of steps times alpha. Remember, alpha is t squared. And number of steps is at most number of choices for Fi, which by the claim is this. So it's at most t squared times this number, which is at 1/4 homomorphism of P2T minus 1 G. Okay, which is less than half of P0. Remember, initially we say P0 has at least half of the homomorphism. Number of P0 is at least half of homomorphisms of P2T minus 1. Then we are done. We delete at most half of the path from P0. So we are left to prove this final claim that there are not so many choices for to embed a union of two disjoint paths. To prove this, we're going to use a lemma. Another homomorphism inequality lemma by Erdős and Szymanowicz, which compares the number of homomorphisms of paths of different length. So this lemma says for any k bigger than L integers, such that k is even, k is an even number. Wait a second. If k is even, is it going to be a problem? Oh, it's fine. Yes. K is even. Then for any n vertex graph G, we have the number of homomorphisms of pk plus 1 G normalized by the number of vertices in G. Now you take its case root is at least homomorphism of PL plus 1 G divided by N. You take its Lth root. Okay, this is the lemma we're going to use. One quick word why this inequality sort of makes sense. Let's do a sanity check that these two things, we can compare them. Well, by Sidorenko, how many homomorphisms of pk plus 1 in G? You have n choices to choose the first vertex. Each step, let's say the graph is d-regular. Each step, you have d choices for the next one. So you have to, first vertex, you have to go k steps. So it's n times d to the k divided by n here, raised to the 1kth power. So what's here is roughly the average degree, d. Same for this side. So these two are same order of magnitude to compare, right? Then the remaining, this proof now is fairly simple, follows from this lemma. Okay, so how do we prove it? Well, we need to show, as I said, number of choices of f, right? Which is collection of these two paths. There are many, at most 2t minus 1 positions for this vertex. So let's multiply by 2t factor. So there are less than 2t choices for the position of the removed vertex A. It suffices to show for every L between 0 and 2t minus 4, let's suppose the removed vertex is at position VL plus 2. So this is the removed vertex. Then the two pieces we have, it's this Fi, what is it? This is PLI plus 1. And here it's P 2t minus 3 minus L, number of vertices. It's easy to check. All right. So this is the one that we replace. Okay. We just need to show no matter what choice of L range over, for each such choice, the number of subgraphs isomorphic to PL plus 1 union, disjoint union, P2T minus 3 minus L in G is at most 1 over AT cubed homomorphism of P2T minus 1 times G. If this is true, multiply by another 2t, cancel out, you get 4 over 2t squared times 1 over 4t squared times homomorphism, which is exactly the bound we want. And this just an application of this lemma. This quantity, the number of such copies, obviously is at most the number of homomorphisms of PL plus 1 in G times the number of homomorphisms of P2T minus 3 minus L in G, obviously. And then we use the lemma of Ehrlich and Shimonovich comparing homomorphisms of paths of different length. This is at most, by this lemma, is number of vertices times homomorphisms of P2T minus 1 in G divided by n to the power 1 over 2t minus 2, right? But we need to raise to power L for this first factor, because before it's like 1 over n raised to 1 over L, right? So we move raise to power L and move n to the other side. Same for the other one, so times n homomorphism P2T minus 1 G and divided by 2t minus 2 raised to power 2t minus 4 minus L. This, if you do some simplifying, it equals to n to the t minus 1, n to the t over t minus 1, homomorphisms of P2t minus 1 G to the t minus 2 over t minus 1. Okay. Sidorenko's conjecture for path implies that we have a lower bound on this. This is at least n times d to the 2t minus 2. N choices for the first vertex in your random graph, and each following step, 2t minus 2 steps, you have every degree many choices to map it to. So this is Sidorenko's conjecture. Using this lower bound, this is at most the quantity we need to prove. We are done. This is at most 1 over, what was the bound we need to prove? This 1 over 16, the number doesn't matter, constant times homomorphism P2T minus 1G. And we are done. Any question? All right. So let's recall this proof. It's actually quite short. The key idea is we have to view grid. We have to grow grid in this greedy fashion, cell by cell, from here to here and here, like this. So that amounts embedding a grid to find a collection of rich paths. How do we find a collection of rich paths? We start with the collection of all paths. If there's a path that does not have many replacements, we delete them. And use homomorphism inequality, we show that the total number of this bad path we delete during the process, it can be controlled. So at the end, we have a non-empty collection. Done. Okay. If there's no question, we're gonna cover one last proof in the two-round part. We give yet a third proof of bounded Shumlowicz on the upper bound on even cycles. Using Sidorenko's conjecture. So third proof of bounded Shimonovich using Sidorenko's conjecture and iterative Cauchy-Schwarz inequality. So the thing I'm presenting here, this new proof, conceptually simpler than the BFS proof, shares some similarity to the second proof I showed last week on C6, but slightly different. It's discovered independently recently by two groups of people, independently discovered by two groups. One is Oliver Genzer and Benny Sudakov, and another group is Jae-Hong Kim, Jung-Kyung Lee, myself, and Tuan Trang. Okay, so two group people. What is the idea? So recall, we want to prove this is big O of n to the 1 plus 1 over k. All right? This is what we want to prove. Idea. The idea, yeah, is captured by these two words. We're going to use Sidorenko and we use Cauchy-Schwarz. Right. Okay. So the idea is if most of the C2K homomorphism are non-degenerate, then we are done. Any non-degenerate injective homomorphism is an actual copy of C2K. So we start with the graph. So we start with the graph, n vertices, and also K almost regular using regularization trick. And the number of edges is bigger than some constants, sufficiently large in terms of K times n to the 1 plus 1 over K. We need to embed a C2K in such a graph. So if the C2K homomorphisms, most of them are non-degenerate, we are done. We're happy. So that means most of the C2K homomorphisms are degenerate. So we may assume we can show that otherwise we can show that most of the positive fraction, not most of, positive fraction of the C2K homomorphisms looks like homomorphisms of this degenerate guy. What is it? It's a C2K minus 2 cycle, even cycle, 2 shorter with the pendant edge sticking out. Okay. So assume most of the C2K homomorphisms are non-degenerate, then we can show somehow that positive fraction of all homomorphisms of C2K are homomorphisms of 2K minus 2 with a pendant edge. So meaning this is roughly the same count as 2K. in terms of homomorphism count. Now we use iteratively use Cauchy-Schwarz iteratively. We can show what? Then we show that, well, actually C2K, minus 4 with 2 pendant edge, then can be shown that is roughly the same as 2K minus 2 with a pendant edge. Their homomorphism counts are roughly the same. Okay, this is roughly the same as 2K, we already said. So this roughly all the way, what's the final case? You keep shrinking this even cycle. At the end, you get becomes 4 cycle, right? With many. What's one more step? 4 cycle, you map this guy and this guy. Becomes degenerate. Map these two. Then at the end, we become these two together, then it just becomes a star, right? This star. We'll prove that. What's the star size? K star. K edges. So at the end, we show that if our hypothesis is that most of the 2K homomorphisms are degenerate, we somehow can show using iterative Cauchy-Schwarz that the star of size K has the same number of homomorphism roughly of order of magnitude as the 2K cycles number of homomorphisms of that. Then we arrive to a final contradiction by Sidorenko. Why? Well, the number of, so we arrive to a final contradiction using Sidorenko. Why? Because we prove that SK is roughly C2K through this long chain of Cauchy-Schwarz. By Sidorenko, we know C2K, the count is n to the 2K, edge density P to the 2K. But we can also bound the number of SK homomorphisms. There are n choices to choose the center. Each of this edge in the star, you have maximum degree number of choices to the power of K. And remember, we are almost K regular. So this is less than, roughly less than. There is a constant K hidden here. Okay, let me write it. And some constant K hidden in here, right? N K plus 1, B to the K, P to the K. Because maximum degree is roughly average degree up to a constant K. So average degree is MP. MP to the power of K times additional power of N. This is the number. Solving this inequality, you get, this will imply that P is less than some constants, 1 over K minus 1. Then the number of edges, that's a final contradiction. Because the number of edges, then n squared times P will be less than n to the 1 plus 1 over K, with a small constant in the front. But we start with a huge constant in the front. That's the contradiction. All right. Any question with this idea? So let me illustrate this idea with, I will not do C2K. I just illustrate it with C8. We illustrate it with C8. All right, so we have n vertex graph G, K almost regular, and average degree is at least C times n to the 1/4. You need to prove this, right? Some constants n to the 1 plus 1 over 4. So average degree more than 1/4. H density is average degree divided by n. C n to the negative 3/4. We need to embed C8. So as we said in the idea, we assume that all the C2K homomorphisms are degenerate. Among all degenerate ones, the largest degenerate copy identify 2 vertices, no more. If I identify more 3 vertices into 1 vertex, map to 1 vertex, this is a smaller, even more degenerate copy. So let's look at the largest degenerate copy that only identify 2 vertices. For C8, there are only 2 kinds. Only 2 kinds of largest degenerate homomorphism. Largest degenerate homomorphism. Which 2? The first kind is you have 1, 2, 3, 4, 5, 6, 7. These 8 vertices, you identify 2 vertices, these 2. If you identify these 2, that's precisely 6 cycle with a pendant edge, where this vertex is this vertex here, right? A different kind is you identify different places. You identify position slightly further apart. Let's say this one and this one. Let's say, yeah, this one, this one. If you identify this, you will get 2 full cycle where this vertex is the one that you glue them together. These 2 are the largest one with the most number of vertices, i.e. Okay. So we first have to show that we don't need to worry about this type. We have to first show that this takes positive fraction of all homomorphism. So this is a single use of Cauchy-Schwarz. Shows that we can bound the second type by the first type. All right. Why is this true? Well, here's the Cauchy-Schwarz. So if you have a homomorphism of this guy, how do we do Cauchy-Schwarz? I draw it by picture. Yeah, what is Cauchy-Schwarz? Sum of AI, BI square is at most sum of AI square times sum of BI square, right? We're going to use this. We're going to do Cauchy-Schwarz through this line. What does it mean? Let me make this red. Let me make this blue. Okay, so this is the red part. This is the blue parts. This is the red parts. Okay, let's call these vertices U, V, W. By Cauchy-Schwarz, well, this is F. What is F? F is a particular P3 homomorphism in G P3 homomorphism, which map UVW to some UVW. Here, VW could be the same vertex, I don't really care. Some homomorphism of P3. And how you obtain a homomorphism of this degenerate copy? Well, you can write it as, let me write it as phi. So this is a homomorphism phi. If you let A phi to be, the number of extensions of phi to 4 cycle to a P4 homomorphism, what's the name? X, Y, V. Okay. A phi is the number of choices to map a P4 homomorphism with m points UV. And B phi is the number of extensions to a P4 homomorphism with m points VW. So V, let's say PQW. Oh, I use P. So Z, QZ. I'm running out of VQZW. Okay. In this way, this left-hand side can be written the homomorphisms of this in G can be written as what? As the sum of overall phi, A phi times B phi, right? How do we find the homomorphism of this guy? You first fix phi. So sum over all phi. You then embed this part, homomorphism, A phi choices. Then you choose this part, B phi choices. Multiply them together. You get a homomorphism of this guy. Okay? Then use Cauchy-Schwarz. This is at most sum of A phi square times sum of B phi square. What is A phi square? Let's draw the picture. So this guy square is at most okay. I delete this part. I don't really care about this here. What is this guy? This guy is sum over all phi. Phi is this guy, A phi square. So we need to do one choice and another choice. That's A phi square, right? So you need to find another one. This is A phi square. And B phi square, same. Times. I don't care about the left part. Sum over all phi, B phi square means I need to do this twice. You can make it symbolic like this. Okay. And look at the both sides. They are both a 6 cycle with a chord and a pendant edge. Every such homomorphism is a homomorphism of 6 cycle with a chord, right? This actual edge is, if you have a homomorphism of this guy, you get a homomorphism of this guy. So it implies that, so what I just showed is that this guy is this guy, right? Then the right-hand side here, this is at most C6 with a pendant edge. square. C6 with dependent edge in G square. There's actually some labeling issue. So there's some constant here in the front, but it's not gonna, it's just a constant factor. So we show that the number of homomorphisms of this copy, largest degenerate one, can be bounded by the first kind. So we may assume the first kind take off a positive fraction of all C2K homomorphism. This implies that this C6 with dependent edge, and the number of homomorphism of this in G is at least some constant factor, positive fraction of all C2K homomorphisms in G. Okay. I will stop here and finish the proof next time. And next time, basically, we're gonna again use Cauchy-Schwarz to show this chain of equivalence, same order of magnitude. And at the end, use Sidorenko to derive the contradiction. It wouldn't take much more time. I don't want to go over time here. Any question?